All right, guys, Math 6500 Logistic Regression. Um, what, uh, what I'm going to talk about now are prediction rules, and what I want to give to you are three possible prediction rules. Actually, there's going to be four, but I have no idea why I'm putting three. Guys, a lot of times in research, we'll talk a lot about effect sizes. And for the most part, what I'm getting ready to demonstrate here in terms of prediction and prediction success percentage of accurately classified cases, as we'll call it, we refer to these things as effect sizes in logistic regression. Now, starting out, the difficulty in making predictions of a binary outcome variable is determining the cutoff. Where typically, whatever cutoff that we set, anything below that is classified as a 0, and anything above the cutoff score is classified as a 1. So possible approaches. Number one, just set your cutoff equal to 0.5 and report it. This works well in certain situations, in my opinion. I don't know if the research actually backs me up on this, but it's my opinion that if the population of interest, if there's a equal chance that our zeros and ones will occur, then I think this is a reasonable approach. And secondly, if the consequences of our decision of incorrectly predicting a 0 and 1 tend to equal out, then I think this is also a reasonable approach. Now, let's think about some possibilities of zeros and ones of where we would use logistic regression. Let's say we're looking at a set of predictors that would determine whether someone survived surgery, where zeros are they did not and ones they did. Well, I think there would be a pretty strong argument against concluding that the cost of incorrectly predicting a 0 or 1 are approximately equal. You would also probably struggle to defend that in the population of interest, all people having surgeries, that it would be equally likely that surviving or not surviving surgery would be the same. So problematic, and same thing in education. I think if we're measuring success in a calculus course, I don't think that success would be equally likely, no matter how high the standards or ridiculously crazy grading practices may be. Second approach would be finding the best cutoff. Couple of approaches here. What you could do is you could take the percentage of ones in your study and set that as your cutoff. That's kind of a reasonable approach. Another best cutoff would be to minimize the difference between sensitivity and specificity. And we're going to talk about that more in just a second. So you guys, I'm fighting a sneeze here. Another possibility is use prior probabilities as your cutoffs. Let's say you're replicating a study, and you found in a previous study that the percentage of subjects who have a particular characteristic, in other words, coded 1 is 0.42. Well, you may use that 0.42 in a prior study. And I say there were 4. Actually, there's not. I think what I did is I actually included my 4th thought in the second thought. So, guys, let's just get busy and see how this all plays out in R. So I think the first thing I would want to do is just illustrate this. where the cutoff is equal to 0.5. So in other words, we're going to predict a 1 if our predicted probability is greater than or equal to a 0.5. And we're going to predict a 0 if our predicted probability is less than a 0.5. Wow, another robocall. Imagine that. This one's actually from Rome, Georgia. Don't you guys get sick of those? I do. So I just went public. Everyone out there now knows that I get sick of these things. All right, where are we? Okay, let's get out of here and let's get into R. R, you can see I've already downloaded or imported the data set that we've been using. So first thing I'd want to do is I need to install a package. And the one that I found, and guys, this is tricky because you know, this SDM Tools package, I can use it on my MacBook Air. I can use it at home, but when I try to use it on Windows, I get a compatibility issue. So it's something that you just have to work out. There are there's just thousands and thousands of hits out there if you do just a very standard Google search on creating confusion matrices and stuff. So anyway, this one seems to work for my computer, so it's the one that I use, and I can easily get a confusion matrix by inserting my dependent variable, calculating the fitted values, and setting my cutoff. It calls it cutoff here, refers to it as threshold. Now when you do it, you get your, oh shoot, wow, that's crazy. I am trying to access a model that I haven't even created yet. Kind of got the cart in front of the horse there, didn't I? All right, cool. So when we run our model, which is always kind of good before you try to do a confusion matrix, that you actually do something. But anyway, we can see that our X1 predictor is significant at the 0.05 level, and our X4 predictor is significant at the 0.01 level. All right, now let's run the confusion matrix. I bet something happens good here now, right? So what we end up getting is we get. It's important that you understand what these values mean. That 58 means that the subject had a value of 0 for the y, and our model predicted a 0. This 12 is the subject had a 1 as a y, and our model predicted a 1. So you can think of these as being accurately classified cases, and these 19 and 9 being inaccurately or not correctly predicted. So anyway, guys, 58 out of 58 plus 12. So that's what, 70? So 70 out of 98. Let's see what that would be. Be 0.714. So we can say that the percentage of accurately classified cases is equal to 0.714 or 71.4%. Now the next thing we'd want to report here would be the sensitivity. And let me jump over here and just give you, I think most of you probably already know this, but if we have our observed values as 0 and 1, our predicted values is 0 and 1. What we call this cell count are our true negatives, and what we call these are our true positives for pretty obvious reasons. And I would refer to this one as a false negative, and I would refer to this one, and others would too, as a false positive. Now, if we let these cells be A, B, C, and D. Sensitivity can be found by taking the true positives over the total number of counts, total number of observations that recorded a y equal 1. Specificity focuses on this column, so it would look at the true negatives over the total number that recorded a 0 as the observed y value. So guys, back over here we can see from the chart, we can see easily that our sensitivity would be 12 divided by 31, whatever that is. And our specificity would be 58 out of 67. Guys, let's calculate those. So 12 over 31. Okay, so it's 0.387. And 58 divided by 67 is 0.866. So let's keep those handy. All right, let's look at something else. Let's look at the percentage of ones that we have in our data set. So I can do a table of y's, and I can see that 31 out of 67. So I'm sorry, 31 out of 98. So 0.316. So what happens if I set my threshold at 0.316? Well, I get a different confusion matrix, and I get a different PAC, and I get a lot of things different, right? All right, it just hit me that what I was writing over there a while ago, you couldn't see. Actually, I have a student coming in. I'm trying to hurry up. So, guys, that's what I was talking about with the observed and predicted. So take a screenshot. Think about what I said. Hopefully you wrote it down in your notes. And then this is what I wrote earlier about the sensitivity and specificity and the percentage of accurately classified cases. All right, I'll try not to do that again because that would be super, super, super confusing. So guys, now if I set my cutoff equal to 0.316, and the reason I did that is because those reported y equal 1 was 31 out of 98. All right. So what do I get there? Already done it. So the percentage of accurately classified cases would be 72 out of 98. And according to the calculator, that would be 0.735. So guys, slight increase over the 0.714 as before. Sensitivity, easy to do, 23 out of 31, which is 0.742. And specificity would be 49 out of 67, which would be 0.731. Guys, notice these are close. So if the objective is to find the cutoff that has the sensitivity and specificity that are the closest, well, it looks like to me that 0.316 is getting pretty close to that. Now I'm going to set another cutoff just for demonstration. I'm going to set it at 0.25. Nothing holy about 0.25, other than I just want to get a third data point. And we can see that the percentage of accurately classified cases are going to be 68 out of 98. Let me go ahead and put that in my calculator. 0.694. And sensitivity is going to be 25 out of 31. 0.806. And specificity will be 43 out of 67. So 0.642. Now, guys, what's all this tell us? What all this tells us is, leads us into something super important. Called an ROC curve. And this is a receiver operating curve. Receiver operating curve gives us a graph of the sensitivity and 1 minus, plotted on 1 minus the specificity. And it allows us to create something called area under the curve that gives us a model diagnostic on the effectiveness of the predictive capability of our models. So guys, let's see how this works. Okay, so on the vertical axis, we'll plot sensitivity. And on the horizontal, we'll plot 1 minus specificity. So we can go from 0.5 out to 1. That should do it. All right, now, before, what we've done is we've looked at some cutoffs. And we looked at 0.25, 0.316, and we looked at 0.5. We had the sensitivity, 0.387, 0.742, 0.806. 1 minus the specificity was 0.134. I think the specificity here was 0.866, easy for you to say. So 1 minus that was so I'll put the specificity out here. 0.269. I hope I'm doing a lot of this mental arithmetic. Guys, hold on, my computer's about ready to crash, and I do not want that. That would not be cool. Alright, let's get plugged up here so this thing doesn't die on me midstream. Alright, cool. Now, so what we would do, the third one, we were looking at 0.806, so 0.642, so if my mental arithmetic is 0.358. Now guys, what we would do is we would go to 0.134, which is approximately, that would be so approximately right there. We would map that to 0.387. We would take 0.269, go up to 0.742, and 0.358, and go up to 0.806. Now, if we were to continue this, we would get something that looked about like this. Not exactly, but sort of. Now, of extreme importance to us would be this area. If we draw the vertical, or not a vertical line, a line from well, the y equal x, let's just call it what it is. And we look at this area, the area under the curve. This gives us a good indication of the predictive capability of our model. Well, guys, it turns out that this is super easy to do in R. So to get an ROC curve, what I would do is access the library. If you don't have it installed, you'll need to. It's called PROC. Get a few warnings, built under a different version, but we'll see if it works. So I'm going to create the ROC curve using the ROC command. So all I have to do here is predict our y's from our fitted values. To get the area under the curve, we get, just put AUC, ROC curve, 0.776. Guys, these are kind of easy to remember, the interpretation of the area under the curve, because it's kind of the same standard we use to grade. Excellent. In other words, A's. Would be 90 to 100. A good model, 80 to 89. An average model would get a C, from 70 to 79. A poor model, which would get a D, would be from 60 to 69. And a failing model would be 59 below. So guys, what we have 0.77. So we get kind of what I would call a C plus model. So it's decently average. It's sort of impressive. All right, but you know, to me, it leads us to possibly want to look for a model that would be more effective. All right, to get our ROC curve, really easy. Just plot the ROC curve, and that's it. That's all we have to do, right? Wrong. That's not what we need to do. Oops. Guys, I'd want to, first of all, put maybe a title on it. So I would say something ROC curve exam success, I believe is what we're, but most importantly, I think that's the way that was. Legacy axis, yeah. Most importantly, we need to add legacy axes. So guys, now we get what we want. We have sensitivity and specificity, and you can see that this sort of looks like what we had before. It's got some ragged edges. Some of them will. Some of them will be smoother. And again, what you're really hoping for is if you have something that is worthwhile to submit for publication, you hope that the area under the curve is in the 0.8 to 0.9 values. So guys, that's all I got. A final parting word, what I would say is, you know, if you run these things, which you definitely should run, area under the curve and ROC curve for a logistic regression model, keep in mind that this is really all tied to the goals of your study. If the goal of your study is prediction, then these ROC curves are of ultimate prediction classification accuracy, I should say. Then these ROC curves, area under the curve, percentage of accurately classified cases, sensitivity, specificity, is of extreme importance. But if the goal of your study is to identify key predictors, then you may not place as much emphasis. So I guess when do you do this? Well, it just depends. All right, guys, that's all I got. Take care.